Hello everyone again, and some of you might be wondering this discussion concerning gravity and also in terms of general relativity that was actually proposed by Albert Einstein. Now, before Albert Einstein came into play, you remember back in the days when we were in grade 9, no, technically speaking, no, grade 9, that would be too early for you to explore really deep, but some students may be curious enough to dive into concepts involving space and time continuum, and some movies do explore that as well, and how you might see some interesting graphics coming from various types of movies that explore sci-fi like Newtonian X with that of Albert Einstein's theories of gravity. Now, this actually comes into play way back in the days where people actually had a really interesting understanding of the universe, and it's great for science because science do evolve, and a fantastic example is when the scientists actually debunked the idea that Earth was the center of the universe and everything was revolving around Earth, to the other way around, where we actually discovered that yes, indeed, it is not Earth that is the center. In this particular case, it is Sun that is the center, and everything revolving around it is, in this case, planets, and Earth is one of the planets. And then coming into 1,000 years later, we actually had another scientist by the name of Newton, who actually built on that particular theory and was able to introduce something quite remarkable, which is called what? Yes, gravity. And gravity was the huge player, according to him, concerning how planets are actually revolving around Sun and also the Moon revolving around planets. For example, we had Sun revolving around the Sun because of gravity, and also that of the Moon was able to revolve around the Earth because of gravity. And so gravity was a huge player in terms of how planets and solar systems work, and that was when until 100 years later, where we had Albert Einstein around the year 1915, who actually talked about something quite interesting, which is called general relativity. And that is where this particular article comes in. And this article was able to bring that history into play, and the article title is "Was Einstein Wrong? Why Some Astrophysicists Are Questioning the Theory of Space and Time." And this here leads us to a little bit of a better understanding of what this concept is about, and also where all this came from and where we're heading towards in terms of the specific type of general relativity that we're talking about. And so, moving really deep into this particular article, it talks about the history and everything surrounding this particular concept of gravity and why some things might not work in terms of Albert Einstein's theory. And this is where some things actually comes into play. How are we going to be able to have conversations involving how things are evolving in terms of ideas, and how this is going to lead to new discoveries and maybe debunk some other theories that was made around a couple of years back. So, looking really deep here, it actually proposed that general relativity or general theory of relativity played a huge role in proving the inconsistencies in Mercury's orbit, and famously confirmed by observation of the solar eclipse off the coast of Africa in 1919. So this is one way where we are able to explore really how this particular theory is applicable to the real world and how it doesn't work in a way, and how can we build on observations that are in science. And then this article then focuses on some of the interesting things that Albert Einstein put forward in terms of gravity, and as a result of the curved system, he said that all objects in the universe sit in a smooth four-dimensional fabric called space-time. Massive objects such as Sun wrap the space-time around them, and so Earth's orbit is simply the result of our planet following its curvature. Now, to us, that looks like an eternal gravitational pull. This space-time picture has now been in the throne for over 100 years and has so far vanquished all pretenders to its crown. The discovery of the gravitational wave in 2015 was the decisive victory, but like its predecessor, one thing is really interesting here, which is how this actually showed the one side of massive objects experiencing this form of general relativity in terms of the smooth four-dimensional system that introduces space and time. However, now diving into quantum, this is where things actually get interesting, because various scientists have brought up the quantum theory in terms of objects and how objects behave strangely in terms of not only not predicting but predicting other quantities. So the more you know more about a quantity, the less you know about the other quantity based on measurements. And so this is one of the huge contrasts between classical mechanics, which was heavily based on Newtonian idea, to more of quantum, where not only Albert Einstein was one of the huge players, but also we had other scientists that were able to have some interesting analogies to prove that, hey, small particles that are way small, almost close to Planck's constant, doesn't actually work really well when you are applying classical mechanics into their behavior, and they behave strangely. One of them involves a vial of poison with a Schrödinger's cat. There's a possibility that you can have a dead and alive cat. On the other side, there's a possibility that you have a poison release or not, or you might have a hammer hit or not. All these possible outcomes are what makes classical mechanics really different from quantum, where in quantum here, we are dealing with probabilities. Probability of one means what? In this case, that it is certain that it is going to happen. However, when you are heading into unknown states where you have, okay, in this case, classical mechanics, there's always going to be one answer, and this one answer is based on a formula. So probability is less of the real world. Probability is more influential when you're dealing with quantum mechanics, and it's one of those interesting, beautiful things that this article actually explores here, not only in terms of the Schrödinger's cat, but also other studies that was introduced in here to record with the smooth continuous fabric of space and time, the gravitational field cannot be in two places at once, which is really fascinating in here, based on how gravity might be a huge difference when you head into quantum state. In quantum state, are we going to be able to have multiple gravities? That will be fantastic exploration of how particles behave based on gravitational forces in the quantum state. And this was where a couple of things involving this particular article touches on in terms of quantum gravity. Is there anything like quantum gravity? Definitely, that will be a huge difference, or that will be a huge contrast from the general relativity that was proposed by Einstein, and may most likely debunk that particular theory, because you can say that that theory doesn't apply to quantum states. And this is where a couple of experiments are coming in down in the future based on how you're going to be using various forms of instruments. Like, for example, we have a collider that is actually going to be used to actually explore all these particular particle behaviors. And also, they also talked about the loop quantum gravity, which is an alternative in this case to this particular string theory failure that was introduced back then. Theory was kind of close a little bit, but not there at all. It needed a lot of, I would say, a tightening up in a way in terms of presenting the ideas. Now, in terms of arguably the most famous string theory, that the idea that subatomic particles such as electrons and quarks are made from tiny vibrating strings, just as you can play strings on a musical instrument in creating different notes. We actually noticed that string theory argued that different combinations of strings create different particles. The attraction of the theory is that it can recoil general relativity and quantum physics, at least on paper. However, to pull that particular rabbit out of the hat, the string has to vibrate according to 11 dimensions. That is crazy. 11 dimensions. Now, this is 7 more than the 4 in Einstein's space-time fabric. As yet, there is no experimental evidence that these particular extra dimensions really exist. Now, it might be interesting mathematics, but whether it describes the space-time in which we live, we don't really know until there is an experiment. So that is a big thing that currently scientists are diving into, and how scientists are going to be able to explore more about all this particle behavior, not only addressing this particular form of space-time continuum that may debunk but may improve on Albert Einstein's theory of special relativity, but also how quantum gravity actually works in terms of small particles or small specific states compared to large states that we all observe in here. So I know this is a long video, but I implore you all to check this video. I'll say this article is in the description down below, and let me hear your thought about this particular setup and format of this particular podcast. Do you think it is kind of fun switching from one camera here, which is right in this particular location? I'm going to switch it here. Voila, there we go, to this particular location right here, and to the screen right over here. I really like this article in a way, because this article really touches on all the history and also where we're currently at in terms of the specific issue involving general relativity, involving gravity when it is in the quantum state, and but also in this case how this article is also able to look at various forms of alternatives and also conflicting ideas involving how this actually is going to play a huge role in understanding how gravity works. So I like this article. I'll recommend it to anyone. You know, this is in the description down below, and the article is actually written by Colin Stewart, and you know what, fantastic job. I have no issues with it in terms of, the only thing I say is, you know, if anyone wants to go into it and want to dive more, get more details, yeah, you can actually go into the specific links in here. Now, the links might be overwhelming for some of you, but some others, if you're really curious to actually dive into this, it's really fun and accessible. And yeah, other than that, yes, please hit the comment down below. Let me hear your thought about this. By that way, I can talk to you soon. Stay smart as always, and believe in yourselves.